So what we're going to talk about is linear impulse and momentum. Can people see my screen okay now?
Yep.
Cool. And I'm just going to walk through this PDF for now, and then we'll have some discussions. So recall that the previous topic that we did was energy, work-energy relationships. And a special case was energy conservation or conservation of energy when we had basically no work done by other forces, namely non-conservative forces. And we derived work-energy relationships by essentially integrating F equals ma. But we did a particular kind of an integral. We sort of multiplied, if you recall, if we multiplied both sides by velocity and integrated. You don't have to remember the derivation, but it's useful to remember that work energy principle is kind of an integral version of F equals ma in some sense. So that's one kind of integration, work energy principle. We can do another kind of integration to get what's called impulse momentum relationships. And this is how it goes. So if you have a single particle, you have sum of all forces on the system equals mass times acceleration. And then you directly integrate both sides of this equation with respect to time. So you have T initial to T final, sum of all forces dt equals T initial to T final, mass times acceleration dt. And then if you integrate acceleration as with respect to time, you get velocity. And you can plug in initial and final times. And what you get here is mass times velocity final minus mass times velocity initial. There should be a bar here, vector velocity. So just summarizing this equation, on the left-hand side, we have sum of all forces integrated over a period of time. And then on the right-hand side, you have mass times velocity final minus mass times velocity initial. So that's this equation. And the left-hand side of this equation is sometimes called impulse. It's called the impulse of force, sum of all forces in this case. So it's called the impulse of this external force or sum of all external forces. And then the right-hand side is called change in linear momentum for the particle, where the momentum is defined as mass times velocity, okay? So you are at least somewhat familiar with these things. This is a vector equation. So the left-hand side is a vector because it's the integral of a vector. The right-hand side is also a vector because it's the difference between two vectors, okay? If you go back to work energy principles, though that was a scalar equation, it turns out, because it sort of, if you remember the derivation, we actually did a dot product to do work. Work is defined by dot product, so the vector became a scalar. So work energy principle is a scalar equation, but the impulse momentum equation is a vector equation. So this equation is called an impulse momentum relationship. And it's true in every direction, basically. So you can write this equation for the horizontal direction, the vertical direction, into the plane, whatever, radial, tangential. In each separate direction, this equation is true, okay? Unlike work energy, where you have to do the total work in all directions, etc. Okay, so this equation, which is called the impulse momentum relationship, was derived for one particle, and we can extend it to many particles. It doesn't matter if you have one particle or many particles in the system, like many masses interacting with each other. Basically, if you write F equals ma for many particles, if you draw a free body diagram for sum of all forces on a particular free body diagram equals, if you have multiple masses, m1, m2, etc., and each mass has an acceleration a1, a2, etc., then the multiple mass version of F equals ma is basically sum of all forces equals m1, a1 plus m2, a2, etc. And then you can integrate both sides and basically have integral of sum of all forces. And then integrating acceleration, you get final velocity minus initial velocity pre-multiplied by the corresponding masses. So you basically get m1 v1 final plus m2 v2 final, etc., minus m1 v1 initial plus m2 v2 initial, etc., if you have multiple masses. This whole thing is called well, I should say final momentum. Sorry, there's a typo here. It should say final momentum, and then this should say initial momentum. So integral of the sum of all forces equals final momentum minus initial momentum, summed over all the masses in the system. That's a true statement. It's basically as accurate as F equals ma, because it's just an integral version, integrated version of F equals ma. And this left-hand side, like I said, is called the total impulse. The right-hand side is called, well, the change, because it's final minus initial in total linear momentum. It's linear because we are considering linear velocities, v1, v2, v3. Later on, we will consider angular momentum. Any questions so far? Okay. Let's do some sort of thought experiments. By the way, this PDF is again online on Carmen, I think. So I can write some notes there if you want. So I wrote down a couple of example special cases. Special case number one is if sum of all forces equals 0 in every direction, right? So you have a system and it's got no net external force on the system in any direction. Then of course the integral of 0 is 0, so impulse equals 0. So that's the left-hand side of this thing. Therefore, the right-hand side, which is equal to the left-hand side, should also be equal to 0, right? So change in total linear momentum equals 0. And this is what we call conservation of linear momentum. It's not generally true. It's true only if the system has no net external forces on it, right? So total linear momentum is conserved only if, well, not only if the net external force on the system is equal to 0, okay? So this is the final linear momentum. This is the initial linear momentum, m1, v1, m2, v2, etc. Any questions so far? Oops, there's a couple of questions there. Yeah, so so I said this is final minus initial. That's a typo, yeah. Final momentum equals initial momentum. It's sort of useful to rewrite this equation, this momentum balance equation, in a slightly different form for some sort of problems or some kind of situations. To do that, we sort of make this new definition. And this is a definition that you guys are probably familiar with. If R sub j is the position vector of a mass m sub j, okay, so just because this V and this R look similar, I've written what this is. This is a V and this is an R. Okay, not to be confused with gamma or I guess other things that may look like this. Nu, I guess, also looks like this sometimes, the Greek letter, unfortunately. Okay, so we define the center of mass. So if you have mass mj have position rj, like the vector position rj, then the center of mass of all the masses combined, like r com, equals m1 r1 plus m2 r2, etc., till mn rn if there are n masses. divided by the sum of all the masses, okay? So that's the center of mass. It's the weighted average of the positions of the individual masses weighted by the masses, okay? So you give credit to each position based on how big the mass is. So if you have a big mass, M1, then the position of M1 is sort of more important than if you have a small mass M2, okay? So anyway, so it's kind of an average position, but it's an average position that gives more credit to the bigger masses. It's not a pure average, it's what's called a weighted average, okay? So that's called the center of mass. You're familiar with it probably. So that's the center of mass position. And then if you differentiate everything, the masses are just constants. So if you differentiate the left and right hand side, if you differentiate the positions, you get velocity. So velocity of the center of mass is basically m1v1 plus m2v2, etc. in the numerator. And then in the denominator, you have the sum of all the masses, okay? This is called the velocity of the center of mass. And then, so once once you have this thing, you can rearrange this equation. You can take this sum of all masses to the left-hand side, to the numerator here. And what you have left here in the numerator is the total momentum of the system, m1v1 plus m2v2. So basically total momentum equals total mass times velocity of center of mass, okay? Momentum of the whole system equals mass of the whole system, all the masses combined, times velocity of center of mass. So this expression is equivalent to saying m1v1 plus m2v2 plus m3v3, okay? This is in a sense the rationale for why center of mass is so important in dynamics. I suppose this and also F equals ma, if you look at F equals ma, this version of F equals ma, you can think of this expression in terms of the center of mass acceleration. Can someone think of this expression on the right-hand side? Can you write that in terms of the center of mass acceleration? What is this right-hand side going to be in terms of the center of mass acceleration?
Would be the sum of all the masses times the center of mass acceleration.
Exactly, that's right, yeah. So if you have a single point mass, then sum of all forces equals mass times acceleration of that one point. But if you have lots of little masses moving around, then the sum of all forces on the whole system of masses, the external forces, is going to be equal to the total mass of the system times the acceleration of the center of mass of the system. That statement is completely equivalent to F equals ma, basically. It has the same status as F equals ma. It's the sort of many body or many mass version of F equals ma. So basically, F equals ma can be sort of nicely rewritten in terms of the center of mass when there are multiple masses moving around. Cool. Okay, so, and in particular, your equation number 3 can be written as total mass times velocity of center of mass final equals total mass times velocity of center of mass initial, okay? Because total momentum is just total mass times velocity of center of mass. This is total momentum, this is total momentum. This equation can be rewritten in this form. Total mass times velocity of center of mass final equals total mass velocity of center of mass initial. It's useful to sort of think about it or keep in mind both versions. Like momentum is this, where it's m1v1 plus m2v2 plus m3v3, etc. Useful to remember that. Also useful to remember that total momentum equals total mass times velocity of the center of mass. Like, however, the individual masses may be moving, they may be moving in like all kinds of random directions. The center of mass, which is going to be some average um, velocity, weighted average, weighted by the masses, will be moving in some direction. And total mass times velocity of center of mass final equals total mass times velocity of center of mass initial. You can cancel the total mass. And this momentum conservation is basically equivalent to saying the velocity of the center of mass final equals velocity of center of mass initial. Okay. Any questions about this? Okay, so we started this special case with saying sum of all forces equal to 0. In other words, we are considering a system where there are no external forces in the system. Of course, if there are external forces, then momentum final minus momentum initial is not 0. It's going to be some integral of this external forces stuff. Basically, it's going to be equal to the impulse. But if the external forces were 0, then final momentum equals initial momentum. And then we basically, by introducing this definition, we've said if there are no external forces, the center of mass velocity does not change, or more generally, cannot change. Does not change, cannot change. Okay. And when we say it does not change, we mean relative to an inertial frame, whatever the appropriate inertial frame is for the particular problem. If we are considering like problems close to the Earth, or like on the surface of the Earth, then it'll be like Earth surface or something like that. But otherwise, it's going to be, I don't know, center of the solar system or center of the Milky Way or whatever. Anyway, so here's an example implication / thought experiment. This is maybe something you're familiar with. If you have an astronaut, that's an astronaut. It's supposed to signify an astronaut because the person is wearing this backpack thingy. And then they're in outer space, like far from gravity, let's say. So sum of all forces on this person is going to be equal to 0. Okay. I should put a little bar on top of the 0 to indicate that it's a 0 vector, just to be, if I want to be very precise with my notation, there's a bar missing over the 0 there because it's a 0 vector. If the left-hand side is a vector, you should always make the right-hand side also a vector. And 0 vector, you put 0 with a bar on top, okay? Anyway, so let's imagine an astronaut in outer space, far from gravity, with no external forces on the person. They're just sort of floating in space. This stuff basically means, this derivation or whatever, basically means that their initial momentum, their final momentum equals initial momentum, their final momentum equals initial momentum, or their final center of mass velocity equals their initial center of mass velocity. Looks like there's an I missing here, initial. Or in other words, the velocity of their center of mass does not change, okay? Another way of saying velocity of center of mass final equals velocity of center of mass initial is basically saying that the velocity of center of mass does not change. It just remains in place, okay? So imagine this astronaut now. Imagine this astronaut. The center of mass is here, like where my, I guess, fingers touch maybe. Let's say they want to move. They can move their arms and legs around however they want. But their center of mass position will just stay in place, absolutely not moving, if they start with velocity of center of mass equal to 0. In other words, if they're initially not moving, they move their arms and legs however hard they want, their velocity of center of mass just remains the same. They cannot move anywhere by moving their arms and legs, right? Does that make sense?
Yeah, that makes sense.
Cool. So yeah, so the astronaut is having fun. Someone says, "Am I having fun, or the astronaut is having fun?" um, okay, cool. Uh, yeah, so astronauts certainly have outer space sounds like fun, but if you cannot go anywhere, it's a bit scary. So how do you move? I guess I reveal the next line. So if you want to move in outer space, what can you do? If there are no external forces, the momentum, the momentum of your system or your body with all the things that you're wearing is just going to be constant forever. So you will not be able to change your momentum. So if you want to go somewhere, what do you do? Um,
You could like throw his backpack or something.
that's right. Yeah. So the only way to do it is to throw something, pretty much. Um, you can, yeah. So throw your backpack or throw your shoe if you're wearing one or whatever, right? Um, because the total center of mass position of all the things that started out with velocity equal to zero. Um, so you sort of draw a circle around this person and say, okay, let's consider all the masses that constitute this person and whatever they're wearing, and the center of mass of that. And let's say for a moment that whole system is starting out at velocity center of mass equal to zero or momentum equal to zero. Um, and that momentum or velocity of center of mass is just going to remain zero forever, um, unless someone pushes that system somehow. Yeah, so you would throw something, um, and if you throw something, the momentum of the system will still remain zero, but because you've thrown something, that thing is moving in one direction, and you would move in the opposite direction. So even though the total momentum still remains zero, you can move. I guess the rest of you can move relative to that object you've thrown. And Mazen says you can exhale air. That certainly works as well. You can blow air, and that can propel you. Um, I guess if you're not wearing a helmet, that doesn't work. That's right. Yeah. Um, Absolutely. Yeah. So, but certainly uh, pushing air out works, or throwing a shoe works, um, and that's how rockets work, right? Uh, so I guess you can imagine a rocket as basically throwing a stream of shoes, like so that you propel yourself in the opposite direction. That's the same principle as throwing a shoe. In this case, it's particles of gas, I suppose, like hot air that you expel. But the center of mass of the whole system remains the same, but the rest of you, I guess, goes forward. So usually astronauts, well, I guess if they're doing a spacewalk, might have a little rocket pack in the back that they can use to uh, essentially expel a little air one way or another to um, propel themselves. Yeah. Someone says, bring a big block and punch it. Yeah. Um, all those things work. Yeah. So let's see. Yeah. So, but it's still important to remember that the whole system still will have the momentum equal to zero. Yeah. Um, Let me see if I have. was just trying to pull up a video, but it's somehow not playing here. I can't find it. But anyway, but I guess you can sort of there are videos on YouTube which I will link to in my I guess after the lecture is over, where there are astronauts who are basically starting in position and without moving relative to the spacecraft, for instance, and um, and then they move their arms and legs around and they just stay in place, basically. Okay, so that's example case number one, when the forces are equal to zero in all directions. Special case number two is the forces are equal to zero in just some directions, maybe one or two directions. Okay. The example that I like to give is a person sitting on ice, basically, and assume for a moment that no friction between the person and the ice. Can people see my screen? Okay.
Yeah, sure can.
Okay. Um, so a person sitting on the ice, zero friction between the person and the ice. So you can draw a free body diagram of the person as a whole. mg is acting downwards, and there is some net normal reaction force upwards, and there's no horizontal force, right? There's no horizontal force either in the left-right direction or into the plane because there is no friction. The only way to get a horizontal force from a flat surface, or like a tangential force from a flat surface, is to have friction, right? So if there's no friction, you try to have some slip against the ice and you just slip. It's not going to produce a force on you. And that's what zero friction means. So there's no friction in the horizontal direction, but there is potentially forces in the vertical direction, okay? But let's look at the horizontal direction first. Because F equal to zero along I, because there is no friction, momentum is conserved. Linear momentum is conserved along the I direction, okay? So in the I direction, momentum is conserved. In the J direction, like vertical direction, we say N and mg, but the normal reaction is actually something that you as a person, as a human, have control over. It has to do, well, if you're just standing still or sitting still, then N equals mg. That's the equilibrium case. But in principle, you can push off against the ground and then try to jump upward, right? That's basically when you're jumping upward, what you're doing is increasing your normal reaction by pushing against the ground hard. And by increasing the normal reaction, you're overcoming gravity, thereby getting an upward acceleration. So in the vertical direction, it's not necessarily true that um, total force equals zero, because N could be made greater than mg, and that's how you jump, really, right? You jump when N becomes substantially higher than mg, that you eventually take off. Okay, so anyway, so in the vertical direction, momentum is not conserved, okay, not necessarily conserved. The person has the ability to move up and down, but in the horizontal direction, they're just stuck in place, except, of course, they can throw a shoe again or use a rocket pack or something like that. Same principle to propel themselves on this frictionless surface. Any questions? Okay, so let me, that's the end of this PDF actually. Let me stop sharing for a moment. Let me go over another problem. Okay. There used to be this game called the Angry Birds where they shot out birds in the air, and sometimes they would split and so on. I guess it's still there, that game. But anyway, I call this the Angry Bird problem. Um, so imagine a single mass flying through the air, and then at some moment, sort of breaking up into three pieces, okay, where the sum of these three masses equal to the original mass. And this sort of breakup happens instantaneously, so to speak, okay? And we'll talk about that in a minute. So you have a single mass, let's say 10 kilograms, breaking up into three pieces, 2 kilograms, 3 kilograms, 5 kilograms. So M becomes M1, M2, M3. You can imagine this to be like fireworks, some kind of explosion, something, okay? Or you can imagine three masses coming together and joining and becoming one mass. That's also like a fine version of this problem. In any case, you're told that before these three masses break up, um, the velocity of the mass is 10 meters per second, and it's going at 45-degree angle, okay? So that's the initial. And then after breakup, you're told that M1 has a particular velocity, like V equals 10 meters per second at 60 degrees, 60-degree angle or something. And M3 is 10 meters per second in the negative 60-degree angle, like something like this. And then you're asked to find what is M2. This is the vector velocity, okay? Vector velocity of the mass M2. And the way to solve this problem, this stuff is like immediately before and immediately after, right? So it's flying through the air. Immediately before the breakup, it's got some velocity. Immediately after the breakup, it's got these velocities. Because if you wait for a while, then of course their velocities will change due to gravity, right? So this is immediately before and immediately after. So here is an important principle. I sort of briefly said the breakup happens over a very short period of time. If the breakup happens in infinitesimal time, what are the implications? Well, first of all, let me pull up the impulse momentum relationship. Okay, so we have this impulse momentum relationship that hopefully people can see, which is integral of all the forces on the system of particles equals final momentum minus initial momentum. Okay. For this system, what is the sum of all forces on that system? What forces are acting on that system external to them, right? Internally, there are some forces, potentially. What are the external forces? Okay, Jake says just gravity. Ayman says just gravity. And that's right. Yeah, so it's just gravity. And Wyatt says drag possibly, absolutely. So wind resistance, drag, gravity, anything else we can think of? Yeah, so those are the two main forces, I would say. And that sort of encompasses pretty much everything that it would experience. And then there are internal forces, right? So there is the mass, which is a whole, and then it splits apart into multiple pieces. That splitting apart, like if it's an explosion of sorts, there is something that is pulling it apart, right? That is a force, but that's an internal force. That'll be a force that acts internally between the two masses or the three masses, three pieces of the mass. It's not an external force. right? So external forces are going to be gravity and drag, like people said. So internal forces you can ignore for this analysis, and the external forces are what we should consider, and there's gravity and drag. That's right. Now we're supposed to say integral T initial to T final gravity plus drag dt. Okay, you're supposed to compute it. We have no idea what drag is going to be. We know what gravity is going to be, but um, we don't really know what the time over which it happens. But we've basically been told, let's say, that it happens in basically no time at all, infinitesimal time, right? 1/100th of a millisecond, something, right? Very, very small period of time. If it happens in a very small period of time, then you're integrating basically some quantity which is finite, right? So mg is some finite number. It's going to be, I don't know, 10 times 10. If it's like 10 kilograms, it's going to be 10 times 10, 100 newtons or something like that, right? So integrating 100 dt, and then you're saying T final minus T initial. So it's going to be 100 times T final minus T initial. But if T final minus T initial goes to 0, 100 times that epsilon basically is going to go to 0, right? So this impulse, it's not that it's equal to 0, but our assumption that it happens in infinitesimal time makes it basically go to 0, okay? So it's a kind of a simplification. These kinds of things don't happen usually in a very small amount of time, but they're just generally much smaller than the changes in velocity in some sense. So you can treat it as a small amount of time, okay? So that's why we actually, in these problems, when you say infinitesimal time, you set integral of a finite force. The reason why I'm saying finite will become clear, like probably next lecture, when we will talk about quote unquote infinite forces. But when we have finite forces, in other words, just like mass, gravity, drag, these forces are not quote unquote large. They are going to be some number, right? They're not infinity. When you integrate finite forces over an infinitesimal time, the impulse is basically 0. And then once you have that, you just use the formula, so to speak. You just use total final momentum equals total initial momentum. But you have to do everything vectors with vectors. Initial momentum equals 10 kilograms times V initial for the mass. It's 10 is the magnitude. The direction is 45 degrees. So you have 10 cosine 45 along the I direction, 10 sine 45 along the J direction. This is the total initial momentum. And then the total final momentum is M1 times V1, M2 times V2, M3 times V3. That's that. You plug everything in. V2 is an unknown. The velocity of the second mass is an unknown, but velocity of the first mass is 10 cosine 60, 10 sine 60 in the X and Y directions. Similarly, for the third mass, it's 10 cosine minus 60, 10 sine minus 60. That's for the third mass. So you equate everything and then basically solve for V2. Any questions about that?
Can you explain how you get the 2 for the final momentum in the front?
This two is just the mass. It's just mass M1. Mass M1, mass 3 kilograms, and yeah, 5 kilograms. Yeah, this is 10 kilograms times velocity. This is 2 kilograms times this velocity, 3 kilograms times this velocity, 5 kilograms times this velocity. Cool. Other questions?
And we would have 2 equations from the 2 components of the I and J to solve for the components of M2.
You can do that in general. In general, yes. In general, if you have like I and J on the left-hand side, I and J on the right-hand side, you can equate the I components, you can equate the J components. That's a general principle that always works. In this case, it will actually be a bit simpler because basically the right-hand side is some vector. And the left-hand side, you just bring all the like the known vectors to the other side. And all you're left with is 3v2, and you just divide the other side by 3 and you get v2. So you can do that sort of more directly. But absolutely, you can write v2 as like v2x and v2y, and equate the I components to the I component of the other side, equate the j component of v2 with the j component of the other side. Yeah. Does that answer the question? Is there any notation we should use for these values like impulse and momentum? I will make a remark with that in my notes, I suppose. I'll have to check what the book does, to be honest. But yes, I think sometimes people use L for linear momentum, I or P for the impulse, and then H for angular momentum. Yeah. Let me make sure what the book does and report that. But I think L for linear momentum and I or P for linear impulse, I think would be appropriate. Yeah, I very often like to just use words. It's just because some of these notations are not necessarily universal. So it's just simpler to write words. Of course, it takes more time to write words, but if you want, just shorten it. I can say IN MOM or something, FIN MOM. That's totally fine. But it's easier for me to communicate when it's just words on the screen. Other questions? I guess we'll do more examples next time, and then we'll look at angular momentum. We will also look at collision problems. And that's where the quote unquote infinite forces will show up that I briefly alluded to. When things are colliding, there are some sort of large forces involved. And there, some of these things get modified. Anyway, so what we did was linear momentum balance today, or impulse equals change in linear momentum. And we shall continue the story next time.